Yeah, basically what I'm going to talk is about coastal hazards in Chile, mainly tsunamis, storm surge, and some ideas on adaptation we've been facing in the last years, especially responding after many earthquakes and tsunamis we've had in the last 10 years, right? So, let's see. Yeah, so, well, first of all, if you know nothing about Chile, Chile is in the other side of the Pacific Ocean. So, well, as you may know, obviously, we're in the Ring of Fire, so we're pretty much affected by earthquakes. We're in a subduction zone, similar as the one that you have here in Chile. And we also are affected by all the possible things that may happen in the ocean, which is actually fully coupled with the atmosphere. So we are affected to storms and that kind of stuff. Well, Chile is very long, and it's not that. Well, its width is roughly 150 to 200 kilometers, so it's basically almost like a big zone. Yeah, one of the largest countries. One of the things that is very interesting is that it ranges from very high latitudes to almost the equator. So we have almost all the planets you may find. Yeah, that's one of the interesting things about the country. So, well, I'm from the School of Ocean Engineering at Universidad de Valparaíso. It's a very strange name, but that's the name of the city. Yeah. And, well, I'm basically a civil engineer, but I did some environmental engineering thing. My major in the PhD was environmental fluid mechanics. And I work with this professor, Professor Patricio, as Professor Lee told you just before. So I'm going to talk about that from that perspective, like civil engineering and hydraulics and all that stuff. So why I'm here? Basically because I'm very interested in what happens in Japan. So I took a leave of absence in the university from December till the beginning of March. And I came to the country of Yoshimigoda and all these people. Yeah. We have to deal with coastal engineering problems all the time, and Yoshimigoda is kind of like, wow. Yeah. So why not coming to Japan and visit you? And also, well, I'm really interested in what Dr. Lee does here in terms of light-tsunami interaction. That was one of the research topics I covered lately in the last, say, couple of years. Now I'm shifting towards other things. Like in coastal engineering, you do lots of things. It's not so specific. And I'm working with Professor Keiji Satake at the University of Tokyo in trying to learn something about inversion of earthquake sources with tsunami data. It's just an excuse to come here and to know something about how research happens here in the US, in Japan, sorry. So, some of the topics, yeah, storms, climate change, tsunamis, and adaptation. That's basically what I'm going to try to cover if I have time. Yeah, and this house was the house that my father used to work in because he was in charge of a club of former Navy officers that they had their club in the coastline, and it was basically destroyed by a storm. So it's kind of we live in. I live pretty close to this area. So this is something that it's always happening, as well as tsunamis. In Chile, we've had 4 large tsunamis in the last since 2006. Yeah, one landslide tsunami in the south. Yeah, that killed killed 10 people. But then we had one in 2010, 2014, 2015. Yeah, and we also had 1960, which is the largest earthquake or tsunami ever recorded in the history. And I know that it caused lots of damage here in Japan as well. So something about the physical setting of this talk. Well, first, I was just finishing this slide in which I went to there is a museum here at the university, a very interesting museum. I was in the morning, and there is this globe or map. I wanted to show the sizes of the countries. Chile is roughly 4,500 kilometers long. Yeah, as I said, from almost the equator to near the Antarctica. And Japan is roughly 2,000 kilometers long, so we are very much exposed to coastal hazards. I was trying to find out the figure of the actual length of the coast in Chile, and it's something like 86,000 kilometers, because we have lots of islands in the south. Yeah, so imagine the amount of problems we have. And the other thing is that this is captured from the Google Earth. It's impressive. We are 17,000 kilometers away from each other, but still things that happen here in Chile may affect Japan as well as the opposite. So, yeah, being the ocean a fluid is very effective in propagating energy from one side to the other. So, well, let's take a closer look to Chile. Well, so you see that you have the desert here. This is the most driest desert in the world. Yeah, it almost never rains here. This is the north. This is Peru, and then you have the other areas of South America, mainly Argentina and Brazil, and some of the largest rivers worldwide, like the Amazonas. Yeah, and here you have the Andes, which is the second highest chain of mountains after the Himalayas. Yeah, and they are formed because we have the Nazca plate subducting beneath the South American plate. Yeah, and so this is basically the Andean chain of mountains, and in the south it sinks beneath the Pacific. That's why we have all these islands and lots of coastline. Right? So we have desert and we have cold, real cold, really cold down here. And in the middle we have some kind of Mediterranean climate. So Chile is a very interesting natural lab to study climate change. Yeah, and also study climate change and its relation with the ocean. Yeah. So this is how you see it from a satellite view. Yeah, well, this part is roughly like here, yeah, in this area. The transition between the middle part of the country, where we have some forests and the desert. Yeah. So, well, this is the type of coast that we have. We don't have large bays as in Japan. We have these 3 bays, important bays. We don't have. And these are the location of some ports that they are, well, almost not protected to wave climate. Yeah, tsunamis and all that stuff. It's very hard to build ports in Chile. Yeah. And these are the kind of activities we have. We are a mining country. This is the export of iron. We also have salmon. Yeah, almost all of our salmon is exported to Japan. Yeah, seriously, this is in the south. This is where the Andes sinks into the ocean.
That looks like that looks like Mount Fuji.
Yeah. We have lots of our mountain Fuji's there, and this is not a big one. They're much larger. And well, so this is my hometown. Yeah, so this is one of the second largest port in Chile. My office is somewhere here, somewhere behind this. So imagine that you have you're studying tsunamis and earthquakes and all that stuff, and you're literally on top of the coast. So it's very interesting. Let's see. So if we talk about coastal engineering, just to give a general point of view, these are some of the variables that we need to take into account when we make a design. Yeah, for example, a port, a coast, like a coastal road or whatever, or an artificial beach. Yeah, you need to know some things, variables about the ocean, like sea level, rise or not, waves, tsunamis, and all that stuff. So in this talk, I'm going to talk a little bit about waves and its relation with storm surges and that kind of stuff, and about tsunamis. Yeah, I'm going to skip the rest. But anyway, it's just to give you an idea that there are lots of things that you have to take into account when you make a design from the engineering point of view. I worked 10 years as an engineer before going to research. So this is coming from my experience. So for example, imagine that you're trying to do something here. This is the coast, very simple idealization of the coast, and you want to build a road or whatever. An outflow or an inlet or a plant, a power plant or whatever. So if you want to, for example, find out what are the loads acting on a structure, you need to know the combination of the different natural processes that sum up to define what's the water level. And on top of it, the waves are going to attack the coast. So you need to know something about the mean sea level, which is not constant, especially if we're considering a design life of structures, which is going to be, let's say, 50 years or even more, like ports can be 200 years. You need to know something about the tides, storm surge, meteor tsunamis, waves adapt, and long waves, and so on. So one of the things that it's different from coastal engineering when you compare it like with hydraulic engineering is that you're, for example, if you're doing something in a river, your most relevant variable is the flow, the stage, what's the flow on a particular section. So it can be almost reduced to one variable, maybe sediments, and then it becomes more difficult. But if you're in the coast, this becomes massively complex because you have lots of variables which are acting. Some of them are very deterministic, like the tide. You can actually predict the tide in, let's say, 20 or 30 years in one point, just by knowing the position of the planets. But there are some which are much more complex, like meteor tsunamis or storm surge, yeah, which are more random. So we find this is already hard. Yeah, so we have multiple variables, and we can play with deterministic models or probabilistic models, and this is well, a complex thing. So let's take a look at storms in the particular case of Chile, and then I'm going to put the storms in context in climate change. So this is one of the typical, this is beautiful. From the fluid mechanics point of view, this image is amazing, because the clouds are tracers showing what's the wind field. So, well, this is the coast. I'm going to talk about a big storm. For us, it's not big if you compare it like with storm surges in, I don't know, let's say in the Mexican Gulf. Yeah, but well, I'm going to talk about one particular storm that we've been studying because it caused lots of damage in central Chile. This is the type of image you may have in a coast. There's a hotel, and well, this hotel was attacked by the waves, and all the facilities in the first and second and third stories were mostly destroyed. Yeah, and this is just a case. But this is a very simple thing to explain to kids what waves are. You need a source of energy, the sun, yeah, which generate winds. The winds, well, transfer their energy into well, locally generated waves called seas, and then they get older. Yeah, at the beginning they are very difficult to understand, like kids, and then they become more ordered, and finally they literally die and transfer their energy to all the other processes like sediment transport in the coast. Yeah, very simple thing, but this becomes a little bit more complicated if we start digging into engineering. So waves in the context of storms, yeah, can be separated into time and space. Yeah, and there are different scales. So swell generation and sea generation offshore, yeah, can take days up to weeks in order to generate. But then you have coastal waters, the waves approaching the coast, they tend to be affected by refraction, shoaling, and all that stuff. Then you have nearshore waves where diffraction and reflection becomes important. And then there's a typo there. Well, and once the wave comes into the coast, it starts interacting, like for example with sediments, what we call morphodynamics, or with structures, with structure interaction. Oh, this is full of typos. I was doing it when I was coming here, so sorry for that. I'm going to fix it and send it afterwards. And then we may also be interested in the relation between the fluid and humans and cars, for example, in a coastal road. Yeah, what's the maximum speed, all the flow that actually a car can stand before collapsing or crashing into another car. And you can even go further and try to understand turbulence in this coastal zone. So this becomes hard, and I'm going to show one very simple example. This is not like advanced research, it's very practical, of how can we deal with all these scales in order to finally understand what's going on here, in the place where we're doing our designs. So, for example, we may start making the analysis on a synoptic scale. Yeah, you can have, for example, atmospheric pressure fields with winds, which will generate eventually waves. This is wave watch 3. We've done some work about this. Then you have to bring this information of the waves to the coast by, for example, phase average models or phase resolving models, like Business type equations or, I don't know, event. And then you can actually analyze morphodynamics or fluid structure interaction or eventually fluid human interaction. That's something, that's a term that I was just trying to put it into words now. Yeah. Okay, so let's take a look a little bit deeper in this. It's not working anymore. Oh. So something happened. The computer died. Oh, there it goes. Ah. Okay. So here. Yeah, so for example, this is part of the work that we've been doing lately. I think there's a video I'm going to have to take out of this. So for example, this particular storm that we studied, and we analyzed the generation of a meteor tsunami, which is a long wave in a higher frequency than the storm surge, but occurs simultaneously. And it's mainly driven by the fluctuations in the pressure in the atmosphere. So for example, this is the track of the storm, yeah, the minimum pressure along the area. And you can see here the high frequency long wave being generated by this storm at different tidal gauges in South America. So, for example, in Callao, which is something like 3,000 kilometers away from the source, yeah, this kind of oh, there it is. Yeah, this kind of perturbation was detected. So even though it's a locally generated phenomena, yeah, it generates either waves, tsunamis, and storm surges that radiate from the source and affect other places. Going a little bit more local, so this is Valparaíso, the place where I live. Yeah, what we actually can do is to get information from wave timecast, all forecasts, and also get some information from buoys, yeah, in order to take that information as closest as we can in order to analyze this particular case. And then we can do like use different grids in order to take this information into more coastal areas. And we can actually make analysis, for example, within the bay. These are many places within the bay. That's my office is here. Yeah, and this is basically the wave height, the period, and the tide level at different times. So we can actually estimate what's the overtopping, for example, in places like this. Right? So then you can go a little bit more in detail, and this is the analysis of that this coastal defense. This is a very famous coastal defense because whenever there's a storm, the journalists go there and start filming what happens because the wind calls, and it's very dangerous. And so this is a physical model that we carried, Chilean hydraulic glove carried out, and we did the corresponding analysis with some sort of open foam type of model. And so, for example, from this type of information, let me show you a video first. It will take some time. So here's the submarine beach, and then you have the structure here. And what we did here was to build an artificial pond in order to capture all the water and estimate what's the volume. Because with that volume, you can actually design all the drains of the coastal road, to avoid actually flooding, right? And you can calculate, for example, instantaneous flooding or the accumulated volume across the on time. So, for example, in this particular case, we are calculating the flow crossing this area, and with that flow, we can also calculate the velocities and see how safe it is, for example, for a person to be here. Yeah, depending on the water depth and the speed. Yeah, and
so did you use the open foam?
It's OLAP foam. It was an adaptation of open foam, with some boundary conditions of waves, and it was generated by Pablo Higueras from the IH Cantabria, and he's now working with Philip Liu at Singapore and in the US.
So they opened the IH phone or something?
Yeah, they adapted the IH phone. Well, no, they adapted the open phone, and now it's called Ola, which in Spanish means wave. Ola phone. Yeah. Okay, so as I said, you can calculate the instantaneous flows at different times, and then the accumulated volume to calculate the drain design. And this one is for safety. For example, this is something very preliminary that I haven't been able to review because it's an undergrad who is doing a very simple calculation. But for example, you can actually calculate with very simple body force diagram. What's the combination between water depth and speed that would make someone, fall? Yeah, very simple. I brought this one because I know that Professor Taro Arikawa has done something with tsunamis here, but I haven't been able to find any paper in the literature that's actually calculating the flow and what's the...
Body forces.
Huh?
Body forces.
No, the flow attacking a person or a car. So kind of empirical approach to understand what's the flow speed that would move someone.
There are some studies, or even physical modeling studies going on in Kyoto University.
Oh, yeah.
Yeah.
Okay, so I have to go there. Yeah, because I know that Professor Arikawa has done something, but I haven't found anything published. Arikawa is in Chuo University. He was at Paris.
Yes.
Yeah. But well, so now you give me an idea.
Also, some hydraulic engineers in Kyoto University, they worked on this kind of the body forces due to the tsunami and even heavy rainfalls.
Oh,
so flooding situations.
Yeah, good. Yeah, very good. Yeah. Nice. Okay, so also what we have done is, for example, make monitoring of beaches to see and test some models. For example, X Beach, which is a standard, it's kind of popular model for to calculate the evolution of beaches because of the wave attack. And in this particular case, what we did was to calibrate the beach. This was the original profile at this place, and this was the final profile. And we calibrated the model in order to tweak some numbers to make it work properly and reproduce the formation of these profiles after the storm. Currently, we just built this flume in our school. We have no experience in physical model, no experience. So we just jumped into the pool without water. Okay, let's do it. Yeah, and what we really want to do is basically, this is also typo here. Is to actually understand something about the structural response of piers under wave attack. So this pier in a little bit south of the place where we live, and they were actually building the bridge, the pier, and it was damaged. So yeah, this is the type of thing that we normally see in Chile. These type of piers are kind of becoming popular because all the shelter areas, not all, some shelter areas in the world are being there's little space in this shelter area, so some facilities are beginning to face the open oceans. So what we really want to understand is what's the structural response of this structure. Okay, so let's see something about climate change. So first, a couple of comments. This is again Valparaíso, and this is a breakwater which was built from 1912 during 20 years, and it was ended up by 1930 something. Yeah, and this picture is recent, so that means that this structure has been there for 100 years. Yeah, this was the way it was built. Yeah, and in those years, Chile was very kind of advanced because it was very connected with the rest of the world. All the ships would come through the Cape Horn and stop in Valparaíso and then go to Asia or backward. But after the Panama Canal was built, all the ships started going yeah, near the equator, and our country just went like. So that kind of thing was done like 100 years ago, but I don't really think we could do it now. Okay, so and that's my daughter, but this is a picture from an artist, the very famous artist. What he did was to drain Valparaíso Bay and show the structure. So this is 60 meters deep from the bottom. So it's like so this is very, very interesting. This is a 7-story building. Yeah, and then so you could imagine that this is almost 1 kilometer long. So probably for Japan it's not that big, but for us it was the largest structure built in the whole 20th century. And you actually go to the coast and you don't see it. Yeah, just like
you are seeing the top, a few meters of top.
Yeah,
and so many concrete blocks in the downward.
Exactly. It's huge.
Have you been to Tohoku Kamaishi port?
No, but I know the story.
Yeah,
I need to.
That is exactly like 60 meters.
60 meters.
Yeah, from the bottom. So similar, probably similar size.
Yeah. Wow. Yeah.
There's a tsunami barriers kind of. But it was broken by the tsunami.
Yeah, I know the story. I know well. That story has been around the world.
The national committee decided to reinforce the block, reinforce the tsunami barrier again, reconstruct it.
Okay.
They decided to reconstruct it.
Yeah.
It's crazy.
Yeah. Wow. But it helped to reduce the flooding. Some studies show that they how can I say it, reduce the tsunami height, also the reduce the arrival times of the tsunami. Yeah. So
but in the end it's like all swapped away. So.
Yeah. Okay. So this is just to say that so when we do coastal work or ports, they're going to be there for centuries or decades, and then climate change becomes really important. Like this is something that's going on now in Chile, in this particular bay. Lots of different designs. This is probably what's going to be built. So what is being built now? It's going to be probably till 22nd century. So this is just a schematics on how do we deal with statistics. So, for example, let's say that we are sitting today here, 2017, and we're designing something. Yeah. So probably it's going to be built 2020, 2025. You know, these kind of projects take between 4 and 10 years to finish. And so it's going to be way beyond 2,100. Oh, how do you say that? It's 22nd century. 22nd century. It's strange. Yeah. So then you may have statistical records of, for example, hindcasting wave or records, actual records from wave buoys. There are some of them which are even going at the beginning of the previous century. So as long as you go way beyond that, uncertainty becomes even more relevant because the information gathered 100 years ago probably was much worse in terms of the quality than what we have nowadays. And if we try to estimate what's going to happen in the future, we also have uncertainty. So we have some data sets from, for example, IPCC or any of these groups that they can even predict what's going to be the wave climate in 2090. That's impressive. Imagine that. You just download the data and you say like, wow, this data, what's the uncertainty with that? It's something that's overwhelming for me. And I'm not a meteorologist or a climate scientist, so this is something like a black box. Maybe you know much more than that. Yeah. It's just to reflect that the uncertainty is almost everywhere.
Some guys are working on the climate change analysis, the IPCC data set.
Oh, yeah.
2100.
Yeah. Okay. So in this context of climate change, if we go again into some of the variables, most of them are affected by climate change. Yeah. Sea level will be affected by climate change, waves, And for example, long waves, which are somewhat related with waves as well, storm surge, and so on, right? So all these static variables, they all of a sudden, yeah, it will change and will be affected by uncertainty. By the way, all these people are researchers from Chile that I work with. So for example, if we try to understand what's climate change in very simple engineering type of approach, and this is probably not so rigorous, we may have a time series of more than 30 years, according to the International Meteorological Organization. More than 30 years can be attributed to climate change. And so we can adjust the trend, for example. This is just an analytic model. This is very, very, very basic, saying that, for example, this time series could be separated in different contributions. Obviously, this is not a sum. Yeah. So you can have a trend. So for example, if we're talking about sea level, we can have the trend in mean sea level, but we can have regular cycles that change the sea level. Yeah. Season, day, even, and the tide, for example. Yeah. Regular because the period is very well defined. You can have irregular cycles. In South America, the El Niño Southern Oscillation is very important. Yeah, and you can have noise which can be associated to instrumental red errors, or even to probably the most interesting thing is that all the things that we don't know. Yeah, that's part of what the scientists should look for. And this was said by Monk, Monk, the oceanographer. I heard one of his talks, and he was saying that there's a documentary saying something like, no, the noises, all noises everywhere.
I'm quite interested in the noises these days.
Oh.
How to separate noise from the signal?
Oh, that's good. We have to talk. And then you can have transient motion. So for example, the earthquake uplift or subsidence is very strong in subduction zones. Yeah. You can have, for example, subsidence. You have the sea level, and then all of a sudden 2 meters of subsidence, and the sea level record will dramatically change. So climate change, climate variability, and, for example, geophysical driven changes. So the thing is that in Chile, we are in a big problem. This is schematics of the seismological network we have. So there are about 535 instruments to actually record earthquakes. Yeah. In climatology, well, almost 2,500 instruments to record rainfall, temperature, flow. So if you were like a doctor, a surgeon, trying to assess this patient, yeah, well, this guy would be kind of comfortable. He has lots of instruments, yeah, here for all these devices. But if we go to the ocean, we only have 40 tide gauges, and we have not a single permanent wave monitoring system. No. No. Only a few, every once and then. Yeah, but we don't have it. But it's like, I don't even know how to say it in English, but we have little grounds, scientific grounds to actually capture information from waves. So, and from the tide gauges, remember this is 4,500 meters long, so it's one tide gauge every 100 kilometers roughly. Yeah? And almost half of them were installed after 2010. Yeah, because of the earthquake. So that means that before 2010 we had roughly 20. And if you want to learn about climate change, you need to have long-term records. So we have really few long-term records. We don't really know what's going on. So in this, what we actually did to try to change some of these things. So for example, in terms of waves, what we did we generated a wave atlas, yeah, and by doing hindcasting, and nowadays we have like 39 years of data where we can actually make a statistical analysis and all that stuff. And we finished this last year, and now we're starting to analyze it. I'm going to show some of these results. Okay. So this is just an example of this type of analysis. This is data of the number of extreme events, meaning storms. Yeah. By extreme events, it's basically saying you have statistics of significant wave height, which is a statistical parameter characterizing the sea state. And you say, okay, whatever goes 2 standard deviations above the mean, then it's an extreme storm, right? So then we counted the extreme, very simple, extreme storms in between 1960 and the present. And in front of my city, there were roughly 50 years ago, 60 years ago, and now we have 20. So there's an increase in the number of extreme events. Yeah, more frequency of extreme events. The other thing is that, so these are the maximum wave heights. This is the trend of the maximum wave heights. Yeah, in the same period, and we've seen that they are actually increasing. We're not doing extreme analysis because then we should pick like each individual storm, but it's just showing the trend that there is also an increase in the intensity of the storms. So more storms and more energetic storms. Yeah, and we've seen a shift in the offshore wave direction. Yeah, wave direction is changing because all the climate system is moving in front of our continent. And that means that if you have changes in the wave direction, you're going to eventually have changes, for example, shifts, rotations of the beaches, and that kind of stuff. Right? So then what we did was to extend this analysis to all the country, since we have this idea all the time saying that we have almost all the wave climates we may find. Well, it's not that, anyway. And we detected that the change, the slope of the significant wave height is all positive all through the country. So the energy of the waves is beginning to be larger. Has been larger, sorry, between this period. And then we have observed the change in direction almost throughout the country. So what I just said before is an evidence of that it's happening almost in all the country. Yeah. So basically we have an increasing wave height, an increasing wave period, yeah, and a shift in the direction. So what we're doing now is to move a little bit forward and try to estimate the return period of flooding in coastal areas. Yeah, this is just an example of one of the beaches in the bay where we are. And so we're trying to move forward to hazard maps. Yeah, this is just a small bit of work, and I think that we should have a big battalion of people working on this, but it's very hard to find people in Chile. But so this is just an idea of what we should do. Sorry. Oh. So we are trying to move forward to generate hazard maps of flooding because of storms. Yeah, we already have done this with tsunamis, but the tsunami hazard mapping in Chile is very basic, deterministic with historical records, no probabilistic analysis whatsoever. And we also have to move into inventory, so basically to evaluate the vulnerability, we need to know what we have in the coast. Yeah, so that's the kind of things. And go to micro-zonation, yeah, defining very locally what are the responses of each individual part of the coast. So other type of analysis we've done is to evaluate the changes in the coastline. So for example, at the same bay again, yeah, we have identified some stable beaches, some of them that are tilting, probably because of the change in the wave direction, and some of them are being eroded. Yeah, and we don't really know if this erosion is due to changes in the wave conditions or in all the other variables that may define erosion. For example, urban expansion here. Yeah, the city has expanded, and the basin, that used to be green, now it's under concrete, so that changes all the dynamics. So that's the kind of thing that we're doing. Okay, let's see a little bit of mean sea level, and this is again I think this is interesting. This is an image showing the typical plot of the predictions of sea level change for the future. So 2100. How do you say that number in years? 2100. 2100. Okay, 2100. Okay, the stratus go up to 1 meter, which is like this. It's not that much. Okay? It doesn't look that much. But if you go to, for example, this is a work by Brooks et al., in which they show all the areas in the world in which the surface is beneath 20 meters. Yeah, going away 20 meters compared to 1 meter. Well, geometrically it's not that important, but you know that there are physics there. So You may see that in Chile we almost have no problem because of the uplift, constant uplift due to the earthquake cycle. Yeah, there are some other areas in the world, yeah, I don't know, Katrina, all this area. And some very well-developed countries like the Netherlands that will be probably able to cope with climate change in the future. But some areas like Bangladesh, which very poor countries, it's going to be a much more way to deal with it. So, as I said, in Chile we have this uplift, almost permanent uplift in this area mainly, where the Andes sinks into the Pacific. Almost no people live here because it's too cold and it's very difficult to get there. Yeah. So here we will probably won't have too much problems in terms of flooding. Yeah, but let's take a look at some of these few sea level records we have. So for example, one in the north, one in my city, and one in the south. And this is the type of behavior we have. Just to show that, for example, in the north, there is a decrease in sea level. Yeah. In places like Valparaíso, you have well, it's very hard to make an analysis with this type of signal. Yeah, and in some of them you may see trends. There's a big change there, probably the offset of the instrument. But this is to show that we are not that clear that sea level is rising. Yeah. The other thing is that these are ENSO years, El Niño years, that generate like, for example, during Niño years, the sea level increases by 30 centimeters, which is, during an ENSO year, it's like, you may see what will happen in the future with climate change. Yeah? It's like a sudden increase in water level. You could, during a year, replicate what will happen like in 30 or 50 years. So I think that there may be interesting things to study in terms of this type of fluctuations. So we believe, I haven't gone through all the geodetic studies that are being carried out. There are some being done now. But we believe that these signals are very affected by all the seismic cycle, which is the post-seismic cycle during the earthquake, the interseismic cycle, which is between earthquakes, and the post-seismic cycle, which is the rebound after the earthquake. So all these things may be affecting the position of the tide gauges, and then they are affecting the record. And also we have the El Niño Southern Oscillation, so this is something that we haven't done, and it's interesting. So, for example, these are the slopes of the sea level signal. So red means increase. Yeah, blue means decrease. So here we see that this mean sea level rise attributed to worldwide average situations, yeah, is far from what's going on in the country. Yeah, almost all the stations are having decreasing sea level, and even have big changes in neighboring stations. This is just looking at the statistics, nothing else, just data. Yeah.
I also do this kind of analysis around the Japan, especially
in
Western Japan. We have similar this kind of results that may be affected by the seismic motions.
Right.
So it's quite difficult to say whether it's rising or falling because of the seismic motions.
Wow.
So so many noises polluted by the seismic noises. So.
Right. And you also have these kind of things that maybe two neighboring stations that they're.
I can show you later.
Wow. This is good. I've been working on this for a couple of years. And you don't have no one to talk with. And then you have these people are talking about these things. So, for example, this is the uplift of 3 meters generated by 2010 earthquake 8.8. Yeah. So 3 meters is according to like average values worldwide. It's like 1,000 years of climate change, but you have it in like a couple of minutes. So the earthquake signal is super important. And you may see, for example, fishing ports that they are not useful anymore because of this effect. So let's see something about tsunamis. Yeah. Okay. So this is an image I found before coming to Japan. This is it was in June 1960. Yeah, like 1 month after the 1960 earthquake. As I said, the largest ever recorded. And I guess that the tsunami is the same. And you can see Japanese researchers. Yeah, this actually this note talks about all these the findings of these Japanese researchers. One was seismology, seismologist. The other one was earthquake engineer, building engineer, and so on. Yeah, and well, and in 2010, it happened that I met many of these Japanese researchers working in earthquakes, tsunamis, and all that stuff. So there has been a connection. And one of the things that Japan is, I guess, it's the third economy worldwide, and Chile is like the 40th, or yeah, somewhere. So you're much more developed, and you can see that in research. So, for example, this thing of having like 15 people working in very specific issue is very difficult to find in Chile. So we have a lot of things to learn from Japan. And after 2010, there was an agreement between the Japanese government and the Chilean government. It was a 5-year project in which Japanese researchers went to Chile and the Chileans came to Japan. So we've learned a lot about tsunamis and earthquakes from you. What have we done? I've been involved personally in 3 post-tsunami surveys. So actually, earthquake, tsunami comes, yeah, you go and try to understand why structures fail. Yeah, why, for example, near the rivers, it's very dangerous to locate infrastructure and so on. And you may calculate run-ups, measure run-ups, water depths, and all that stuff, and then get databases that will be used by other people or even us to validate our models. So this is just like a reflection. This is a picture where you can see adobe, one of the type of structures that we use regularly in Chile, old-fashioned type of structures. Then reinforced concrete and wood. Wood, if it is affected by the tsunami, obviously it goes. And the reinforced concrete has good performance. And this, which is a kind of picture for a book explaining 3 things, yeah, was just a picture. But for example, in Japan, for the 2011 event, you have a record of 250,000 houses in which the damage is related with the water test. So imagine, this is just a picture. Oh, yeah, interesting, but we cannot do science with this. So that's the kind of things that I think that in Japan has been very disciplined in order to gather all this information and share it with the rest of the world. Yeah, same with tsunami forests. What's the role of tsunami forests? You know that tsunami forests are aimed to basically get energy from the flood, from the flow, and then reduce the velocity mainly. And I think that this is a flow rate measurement. I don't know how you call it. This is a device that rotates with the flow, or well, it should be with the flow, so the wind doesn't rotate. And it's in the system.
Measuring something like hydrometers or
something like that. Yeah, and it's located in a base which I just guessed that when future tsunamis comes, at least with the rotation of this, you're going to be able to calculate the speed. Which someday, like, I found it like, wow, this is and it's very simple. Why didn't we think of this before? So yeah, that was what I wanted to say. Thank you. Now, questions?